Hello, in this video I will discuss how you can visualize basic properties of determinants and how you can geometrically justify those properties and see that they are geometrically pretty obvious, even though they don't look so obvious, not at all obvious, when you show them algebraically. For that purpose, I assume that you watched the previous video about linear transformations and how you can visualize definition of matrix of a determinant, of 2 by 2 determinant and 3 by 3 determinant. And so let's get started with the first property. The determinant of A times B is determinant of A times determinant of B. Well, if you try to show that algebraically, it's not that obvious, but geometrically it is pretty obvious once you understand the geometric interpretation using linear transformations of the product of two matrices. So let's see, we have linear transformation L1, and that means that L1 of U is some matrix A1 that represents that transformation L1 times vector or point U. And another transformation, call it L2, so that L2 is represented by some matrix A2. Okay? And there is a pretty easy interpretation of the product of the two matrices, and I will write A2 on the left. Okay, so how do we interpret this in terms of linear transformations? Well, it turns out it's going to be a matrix that represents composition of these two functions, of these two transformations, L1 and L2. Composition of two linear transformations is another linear transformation. It's easy to see by representing it as a product of matrix with the vector, which is the input vector. So let's take arbitrary vector u, and what is the composition of L1 and L2? Well, I take arbitrary vector u and I first attack it by L1. So that's actually, I have L1 of u, and whatever the result is, I attack this result by L2. So the result of L1, sorry, this is arbitrary vector u. L1 of u, that's A1 times matrix, column matrix U. So that's A1 times U. But what is the image of this garbage under L2? Well, the image of any vector under L2 is matrix A2 times that input vector. So if this garbage is my input vector, my output under L2 is going to be matrix A2 times this garbage A1 times U. Now, by associative law of matrices, you can write this as, I can first multiply A2 with A1, and whatever the result is, multiply it by U. Okay? And now you see that the image of this transformation L1 composed with L2 is actually can be represented. Sorry, what were you saying? So the transformation L1 composed with L2 can be thought of as a linear transformation represented by this matrix A2 times A1. Okay, and that's another reason why product of matrices, the way we define it in seemingly initially weird way, it agrees with this composition of linear transformations. And now it should be clear what determinant of A2 times A1 is. Well, The way we discussed in the previous video, determinant of any transformation is a measure of deformation of the plane, in this case plane, but also in 3D space, under that transformation. And suppose that L1 deforms space by doubling its each region, and L2 it's by doubling any area. And suppose that L2 triples the area. So you first double the area and then triple the area. So as a net effect, at the end, you will have area that is 6 times bigger than the original one. Okay? And so doubling area, that's determinant of A1, the measure of deformation under L1, that's doubling, so that's determinant of A1. And after you are done with that, then you need to apply L2, which means you need to triple the area. And so that means the measure of deformation under L2 is determinant of A2, and that is factor 3. So in total you double and then triple, so in total you multiply by 6. And so in general you do have determinant of the product is product of determinants. Okay, now these are two real numbers, so I can flip them because this is a product of two real numbers, it's commutative. This is not commutative, but these in general, these do not need to commute, but these two do commute, and so you have, so if instead of A2 I denote it by A and A1 by B, I exactly have this rule. So it's geometrically obvious. Doubling and then tripling, that's multiplying, scaling by a factor 6. Okay, that's the first rule. Now, if you have a matrix that represents some transformation L, and that matrix is A, B, C, D, that's matrix A. What is the transpose of that matrix? So I take rows, convert into columns, columns into rows. So first row becomes first column. So AB row becomes AB column, and second row CD becomes second column CD. Okay? Determinant of ABCD is AD minus BC. Determinant of the transpose is AD minus BC, so it's the same. Algebraically, it's easy to see, at least for 2 by 2 matrices. It is more subtle to interpret it geometrically, but it can be done, but I will not discuss that. But based on this, you see that the determinant of A transpose is determinant of A. And now, to show how determinant is affected when you apply row operations, which you needed for solving systems of linear equations, instead of discussing how it affects row operations, I can take corresponding column operations, and then if I justify column effect of or change of determinant under column operations using this property, the same effect works for corresponding row operations. So if I swap first and second row, first and second column, and see how determinant changes, then determinant when under swapping first and second row, the change of determinant is in the same the same. So the effect is the same as for applying that operation, swapping first and second column. And similarly, multiplying column by some factor, whatever change happens, the same effect is when multiplying row by the factor, and similarly multiplying column by some scalar and adding to another column. So that effect is the same as effect multiplying row by the same scalar and added to another row. Okay, so let us discuss those three properties, and using this identity for transpose matrices, I will just discuss columns because it's easier to see with columns. So my matrix A, B, C, D is matrix of some linear transformation. So first column is L of E1, second column is L of E2. The images of E1 and E2, I'm using notation from previous video. I assume you watched that video. And now the determinant of this matrix is actually, in magnitude, is the area of this parallelogram, this L of E1, that's the image of E1, and image of E2 is the image, so image of E2 is this L of E2. And the orientation of this transformation determines the sign of determinant. In this particular picture, I have 0, E1, E2, and I mapped them to L of 0, 0 under any linear transformation, mapped E1 to L of E1, and mapped E2 to L of E2. Now, in this particular picture with this L of E1 and this L of E2, so I did not change orientation because this is positive orientation, 0, E1, E2. So I'm going counterclockwise, which we call positive orientation. And this one is 0, L of E1, L of E2. So I'm again going counterclockwise, sorry. So that is positive orientation. So I did not change orientation under this transformation L. Now what happens if I swap first and second column? Okay, I will get matrix. First column is BD, second column is AC. Well, this is the image of E1 under some new transformation represented by this matrix, and this is the image of E2 under that same transformation. Okay, let me call it L star. And now, how does that affect determinant? Well, I will look at this. This triple is triple that I use to determine orientation of transformation L. But to determine orientation of transformation L star, I just take L star of 0, that's 0, L star of E1, L star of E1, and L star of E2. But L star, L star of E1 is BD vector, that's L of E2. Okay, this is L of E2. And this L of E2, L star of E2, that's the second column, that's AC, but that's L of E1. So this is L of E1. So what I did, I just swapped these two vectors. So instead of going tuk, 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 so from 0 to L of E1 to L of E2, I need to go from 0 to L star of E1, which is this point, and then to L star of E2, which is this point. So I'm going in the opposite direction. So I flipped the orientation. So in this particular example, as I said, L is of positive orientation, but actually it can also very well be of negative orientation, but the point is L star will be of opposite orientation than L. So if L was negative orientation, L star would have been positive orientation. Okay? In any case, that means the determinant of matrix represented by L, that's this one, so I will call it matrix A, and this is my matrix B. okay, this is matrix B, I see that they have different sign. So determinant of A or actually determinant of B has opposite sign of determinant of A because they represent transformations which are of opposite orientation. But what about their magnitudes? Well, you still have that measure of deformation B is actually the very same parallelogram. It's just that now my first vector is this one and my second vector is this one, but when I make a parallelogram over those two vectors, I still get the very same parallelogram with the very same area. So that means that these two guys are the same in magnitude and of opposite sign. So in other words, determinant of B is minus determinant of A. So it's pretty geometrically obvious. Now, of course, algebraically, it's easy to prove the determinant here is minus determinant here. Algebraically, it's easy to prove. But it's not at all easy to prove, so trivial to prove when you have 3 by 3 determinants and when you swap two columns. But it's now from here the very same geometric idea works also for 3 by 3 matrices. Remember, 3 by 3 matrix represents linear transformation in 3D, and now swapping two columns means that actually you get orientation, you get the transformation which deforms the space with the same magnitude. So because the volume of parallelepiped represented by L star is the same as volume of parallelepiped represented by L, those are actually the same parallelepipeds. It's just that the sides, the way you count them, the way you list them, actually changed the orientation, so the determinant changed the sign, but in magnitude it is the same. So it's pretty obvious that the same rule works in 3D, but algebraically is not that trivial to show that. Okay, that's first column operation. Now corresponding row operation, I mean swapping two rows. Well, it works the same. I mean, the same is with the row operation, swapping two rows, because determinant of transpose of a matrix is the same as the determinant of that matrix. So row operations, swapping two columns operations now become under transposition, become swapping two row operations. So the effect of determinant is the same. Okay, now what about scaling one column? So suppose I have transformation L represented by this matrix, and now suppose I multiply, let's say, first column by some scalar, non-zero scalar k. So I have first column is ka kb, and ka kc, and this one is bd. Okay, what's the effect of that? Well, let's say k is scalar 1.5. So this is my AC vector, okay? But what is vector ka kc? Well, I multiply this vector by a factor 1.5. So that means I stretched it by a factor 1.5. So let's say this is midpoint. So somewhere here, okay? That's L star of E1, okay? And L of E2, L star of E2 is the same as L of E2. That's the same vector, BD. That's this one, all right? What's the effect? How does determinant change? Well, that means how does this area of parallelogram changes. So this parallelogram has area which is deformation under L, and the area is the magnitude of determinant of A, the way we saw it in previous video. And now, since I stretch the base of this parallelogram by a factor 1.5, the area of parallelogram is 1.5 the area of this parallelogram. In other words, by the same factor k. All right, so it's pretty clear that at least as long as you stretch it by some factor k, so that means multiplied by some positive number k, you have determinant of b is k times bigger than determinant of a, or k times smaller. So if the k is, let's say, 2/3, so I get here, so my parallelogram shrinks by factor 2/3. Now what about if k is negative? Well, when k is negative, let's say k is negative 1.5. Well then, instead of 1.5 times vector AC, so that instead of this point, I have negative 1.5, so that's, I flip it on the opposite side, and my parallelogram now will be of the same area as this parallelogram. That's, I think, pretty clear, but I will flip the orientation, and so that means the magnitude will be just like the magnitude if k was positive, but I will change the sign, and because k is now negative, so that just means multiplying by factor k, or in other words, multiplying by negative absolute value of k, which is in case when k is negative, that means multiplying by k. Okay, that's for multiplying arbitrary column by non-zero constant. And now using the fact that determinant of A transpose is determinant of A, that means multiplying any row by non-zero constant affects determinant exactly in the same way as here. And lastly, last property. So what happens if instead of this matrix, I have a matrix obtained from this one with, I don't change anything in the first column, sorry, this is C, but the second column, BD, gets, actually it's not BD, I add first column multiplied by K. So I have plus KA and plus here KC. Okay, what's the effect of that geometrically? Again, algebraically, it's easy to see, at least for 2 by 2. It's less easy to see, less trivial to see for 3 by 3, but the very same geometric idea works for 2D and 3D. So that's why I'm trying to help you visualizing all these properties of determinants, because then they become easily geometrically obvious, I mean geometrically clear in 3D. So, all right, so I have AC, the L of E1 is AC, and L star of E1, that's the same thing, all right? But I have here, this is my image of E2 under L star, okay? Now, L star of E1 is the same as L of E1, so I have this now this is not L star of E1, this is L star of E1, which is the same as L of E1, okay, here. But now suppose that my factor K is, by which I multiply first column, is, let's say, 1.5. So this is K times L of E1, in other words, K times vector AC. And but I have that vector K A K C, and I add vector BD. So this is my K A C, K A K C, and this I add vector BD. That's this one. And so when I add them, so that's adding this vector with this vector, I get the vector, the sum. Oops. The sum is this vector. Okay. Actually, you know what? I think I would, instead of k being 1.5, let me take k being some smaller number, 2.2 let's say 2/3, so I shrink. So instead of L of E1, I take here, that's k times vector AC, in other words, k kc, so that's 2/3 of this vector, and then I add BD, okay, all right, and I get this point. So that's my L star of E2. So this is L star of E2, and this vector here is L of E1, which is the same as L star of E1. When I now focus on L star, I have this vector, that's L star of E1, and this vector. And now the deformation that I have is represented, the amount of deformation is represented by the area of the parallelogram over these two vectors. So that means this parallelogram here. Okay? The reason why I changed my mind, instead of k equals 1.5 to k equals 2/3, is because if I chose k equals 1.5, instead of having this vector, this guy would have gone here, and my parallelogram will be too slanted for you to actually see what is going on. I mean, it's nothing wrong, but it's better to have 2/3. Now, what's the area here of this parallelogram? Well, and how do you compare the area of this parallelogram with the original one under transformation L? Well, under transformation L, we had, so maybe I should use red chalk, okay? So this is my original one, and now I have this one. Well, the base for the two parallelograms is the same. That's this side, and the height is the same. And actually, the area of parallelogram is, of course, base times height. Just take look at this rectangle. Its area is this. Well, actually, I should draw like this. So I have rectangle here and some parallelogram. So A times B. If this is A, this is B. Then the area of this rectangle is A times B, and the area of this parallelogram that has the same side as the rectangle is going to be, well, these two triangles are congruent. If I cut here and glue it here, you see that the area of parallelogram here is the same as that of a rectangle, so it's a base times height. And so there, this parallelogram can be any, so I can take any other parallelogram over the same base and with the same height, and it's going to have the same area. And so you see here that two parallelograms with the same base and same height, so they have the same area. In other words, if this is my matrix A and this is my matrix B, determinant of B, at least in magnitude, is the same as determinant of A. And actually, it's not difficult to see that in fact the orientation of L star is the same as orientation of L. So in other words, these two have the same determinants, same not just in magnitude but also in sign. All right. Now it's easy to see that actually instead of parallelograms, you will have parallelepipeds, and multiplying one column in 3D. So if you have 3 by 3 matrix, it's not so obvious to show that when you multiply one column by some factor and then add to another column, you get the same determinant. Determinant does not change, but geometrically now it's pretty clear, not so difficult to see, that now you have a parallelepiped representing the formation under matrix A, which is now 3 by 3, and its volume is the same as parallelepiped obtained by multiplying one column by some factor and adding it to another. You will get some parallelepiped slanted comparing to the first one, but over the same base, so, and of the same height, and so that means of the same area. Okay, and the orientation does not change, so the determinants are equal. So I hope these two videos help you visualize determinants, matrices, and also get you some basic understanding and basic intuition behind linear transformations, which is useful for chapter 4. Okay, I hope you enjoyed these two videos. Bye.